Here we go. We are going to calculate the volume of the solid obtained by rotating the region under f of x is equal to sine of pi x. Okay, so here is a segment of that graph about the x-axis. We're only doing it between 0 and 1/2. Okay, we're only doing it from here to here. So we are taking the region. Let me not do it that way. We're taking the region under the curve, so between 0 and 1/2. So we're taking all of this right here, and we're going to rotate it around the x-axis. So when we're setting up these problems, when we get to the math part, similar to our cross sections, I encourage you to draw some segments in here, and these are representing the radii of your circle. So let me just show you using this model right here how this happens. So if I take this region and I revolve it, you can see what's happening here. The curve is spinning around the x-axis. And then this goes really fast, but I can spin it around so you can see it kind of creates this cone-like shape. It's got a flat bottom there, and it has a curve there because is that what? We could estimate the volume of a Hershey Kiss, absolutely, using calculus.
That's not enough questions.
So I may have to bring in some Easter Hershey Kisses when we come back. Yeah. Monday I'm not going to be here. You can come if you want to. How about the Tuesday after Easter? We'll look at this. But anyway, so I put a couple of illustrations on here so you can see in 3D view what's going on. But let's do the calculus behind this problem, okay? So volume is equal to pi times the integral from our interval is from 0 to, you can do 1/2, you can do 0.5, it doesn't matter, of the radius squared. Well, the radius here is that curve, okay? The radii are the curve sine of pi x, and we always square the entire quantity. This one you got to rely on your calculator to do this one. Okay, we can't do this with U substitution or anything like that. So you put it in your calculator, and when you calculate the value of that integral times pi, anybody doing it? Size working on it. Pi over 4. Okay, that is equal to pi over 4. Nice, pretty amount there. Okay, pi over 4. Now, some of these we are going to be able to do by hand. This one we just can't because it's the trig function squared. We don't have the derivative of sine of pi x in our problem. So we have to use our calculator to calculate the value. But it ends up being just pi over 4. Okay, let's look at another one. Let's calculate the volume of the solid obtained by rotating the region under g of x is equal to 8x cubed about the x-axis between 0 and 1/2. So again, this time though, the region under the curve from 0 to 1/2, it's a smaller portion, I think, than under our trig graph there. We're just talking about this region. That is the region that we're rotating around the x-axis. So we're going around the x-axis, so always draw a segment or two from your curve to the x-axis. And we can see that these radii are just dictated by the curve. You've got the three-dimensional figure there. Okay, so let's set this one up. The volume is equal to, it is always pi. It's always going to be pi because we're always talking about these are circular cross sections that we're summing up. So pi times the integral from 0 to 1/2 of our radius. Our radius is the curve, 8x cubed squared. Pi r squared. You're always focused on the area of a circle, pi r squared. Now, this one we can do by hand, so let's just do a little bit of practice here. If we're squaring that, we got to square the 8, and we have to square the x cubed. So that's 64x to the 6th. I know, looking really nasty, but it's not that bad. We'll be okay. All right, so if we integrate, we add 1 to our exponent, so we get 7. We divide by the new exponent. We're evaluating from 0 to 1/2. So we have 64 pi over 7 times 1/2 to the 7th. We don't have to worry about 0 because when we plug in 0, we get 0. All right, 1/2 to the 7th, you raise 1 to the 7th, you get 1. 2 to the 7th, let's see here, 2 to the 5th is 32, right? Yeah, 2 to the 5th is 32, so 2 to the 6th is 64, so 2 to the 7th is 128. 64 over 128, 1 over 2. 64 over 128 is 1 over 2, so we've got pi over 14. Pi over 14. So, started out looking a little nasty, but really not too bad. All right, so that is the volume of that solid. It should make sense that this volume is smaller than the previous volume. The region appears to be smaller, and if you look at their three-dimensional figures, I know I don't have them on the exact same scale. This one's blown up a little bit more, but this solid should look smaller than the other. Okay, now, what if we want to calculate the volume obtained by rotating the region between sine of pi x and 8x cubed about the x-axis, okay? So let's just think about this for a second. This solid was pi over 4. This solid was pi over 14. Now we're talking about the region between these two curves. So we're talking about this. Okay. Taylor said, tell me it's not as easy as just subtracting the two. It really is. It really is. Because it's like area between two curves. You take the area under the top curve and you subtract the area under the bottom curve. We're just talking about volume. We've just taken area and made it three-dimensional. So yes, since we've already calculated those volumes individually, then it is just going to be pi over 4 minus pi over 14. Let's see here, that's not too bad to get a common denominator. It'd be 28. So 7 pi, 5 pi over 28. 7 pi minus 2 pi is 5 pi. 5 pi over 28 would be the volume of that solid. Now, what if we were doing a problem and we hadn't already calculated the individual volumes? Okay, what if we had not calculated the individual volumes already? It would be the integral minus the other integral. So if we want to express that in one smaller integral, we would take the top curve, was that f? Yeah, okay. The top curve squared minus the bottom curve squared. Okay, or the outer radius minus the inner radius. You got to find the area of the outside circle and subtract the area of the inside circle. You only need one pi that's in front of them because that pi would get distributed to both of them. So you only need the one pi, but that's what we would do. It's the outer radius squared minus the inner radius squared if you hadn't already calculated them individually. Okay? All right. So here is a picture. I didn't print it on your paper, but here is a picture of this region. I tried to get kind of two different views of it. The outside over here on the left does look like the region, the first region that we had, because that is the curve that's on the outside. The inside, I don't know if you can kind of see on the picture, it kind of dips in towards the origin. It's got a curve to it. I don't know that you can really see it there on the projector, but it is kind of curving in as opposed to being a flat bottom like the first one that we did. Okay, and the volume is 5 pi over 28. That is the volume of that region. Okay, so here is the formal example there of figuring out the area between two curves. We do call it an annulus. An annulus is the mathematical term for what's going on here. We'll call it a washer instead because it looks like, like a washer that you use with a screw. Kevin knows what a washer is. I don't know about the rest of y'all, but he knows. Okay, so like I said, here it is. Outer radius squared minus the inner radius squared. So your top curve squared minus your bottom curve squared. So let's do another problem like this. Okay, find the volume V obtained by revolving the region between x squared plus 4 and y equals 2 about the x-axis between 1 and 3. So volume is equal to pi times the integral from 1 to 3, outer radius squared minus inner radius squared. Outer radius squared minus inner radius squared. Now, they set it up for you. They gave you a picture, but if you're struggling with figuring out what goes where, because we are going to make these a little bit more involved, start with the axis that you're revolving around and draw a segment to the furthest curve away. That is your outer radius. Start on the axis that you're revolving around and draw a segment to the furthest curve away. So that is always going to be your outer radius. If you're trying to figure out which one's the inner radius, then again, start on the axis you're revolving around and draw a segment to the closest curve, and that's always going to be the inner radius. If we're doing it around the y-axis, then yes, it would be different. We would not want to do this one around the y-axis. Right, yeah. So this one would not be one that we would be revolving around the y-axis. We will look at an example like that, so just hold on to that thought for a minute. But yes, it would be completely different the way that we're drawing it. All right, so let's compute this one. We need to FOIL x to the 4th plus 8x squared plus 16 minus 4. So 16 minus 4 is 12. We need to integrate. Do not forget the integration step. X to the 5th over 5 plus 8x cubed over 3 plus 12x, evaluating from 1 to 3. So 3 to the 5th. Ooh, 3/4 is 81, so that one's 243. 3 cubed is 27. 27 times 8. I'm not going to try and do that in my head. 56. 216. 216 over 3 plus 36 minus, plug in 1. This one's easy. 1/5 plus 8 over 3 plus 12. Okay, before you try and get a common denominator for the whole thing, go ahead and combine the ones that have the same denominator. So 243 over 5 minus 1 over 5 is 242 over 5. 216 over 3 minus 8 over 3 would be 208 over 3. And 36 minus 12 would be 24. It would not be impossible to find a common denominator. Obviously, the common denominator is 15, but at this point, I'm just going to use my calculator. Okay, so that gives us 2,126 pi over 15. I started to say 2,100 and it just came out as 2. Okay, so you will end up with some kind of weird answers with these. I'm not going to lie. Usually, always, there's going to be a pi, because there's always a pi in front. The only time you wouldn't end up with a pi is if for some reason it cancels with something about your curve. But 9 times out of 10, the answer is going to have pi in it. Okay. Let's look at another example. Okay. So stick with me on this one. Similar idea. We are taking the area between two curves here, and we are rotating it, but we're not rotating it around the x-axis. We are rotating it around the horizontal line y equals -3. Okay, we're rotating it around the horizontal line y equals -3. So we've got to figure out what's our outer radius, what's our inner radius. So this is where you really need to draw the segments to help you figure this out. Okay, so let's go ahead and start though. We know that it's going to be the volume is equal to pi times the integral. They showed us in the picture that they intersect there at -1 and at +1. Just keep in mind, if they don't give you a picture, if they don't set it up for you, set the two curves equal to each other, solve for x. Okay, so we got to figure out what's our outer radius. So start on the axis that you're rotating around and draw a line to the furthest curve away. Okay, draw a line to the furthest curve away. So part of this segment, part of this radius is just the y value, right? That part that I just highlighted in green, that's the y value. But it's got this little extra piece right here. Now, sometimes it's helpful to draw more than one, just to give yourself an idea of what's happening every time. Okay, so let me just draw another one here close. I've got the y value. The y value part changes. It's a little bit shorter for that second segment that I drew. But how about this other part? Does it change? No. What is its value? Always. How long would this part be? 3. So the axis down here is at -3. So to get from here to the x-axis, this part is always going to be 3 units. So my outer radius is my curve, my y value, plus 3 units. Because the green segments are always dictated by the y value, and then I've always got this extra 3 units here on the bottom, and I'm adding them together to get that. Okay. Yeah, well, yeah, I can. Yeah, Absolutely, you can combine the 4 and 3. I'm just setting it up right now. Okay, minus my inner radius. Okay, let me use a different color here. My inner radius, start on your axis of rotation, draw it to the closest curve. Put you a couple there so you can see them. Okay, this part of it, just like before, that green part, that is dictated by the y value, or the curve, the function. The other part is from here to here, and it's always the same. It is also 3. So my inner radius is my x squared plus 2, and I'm adding 3 to that as well. It's my y value plus whatever the distance is from the x-axis to the axis of rotation. And yes, absolutely. Combine the 4 and the 3, so 7 minus x squared. Combine the 2 and the 3, so x squared plus 5. It's going to make your life easier when you get ready to FOIL here. So when we FOIL 7 minus x squared, we get 49 minus 14x squared plus x to the 4th. We are subtracting, so make sure you put a set of parentheses. X squared plus 5 squared would be x to the 4th plus 10x squared plus 25. Combine like terms before you integrate, or else you're going to be double integrating things. X to the 4th minus x to the 4th cancels. Yay, we don't have to deal with x to the 5th in our evaluating. Okay, we've got negative 14x squared minus 10x squared, so negative 24x squared, and 49 minus 25 plus 24. Now, if you really want to get smart and save yourself some trouble, how about you factor out a 24? And a negative 24 at that. Okay, both those terms have a 24 in them, so I'm just factoring out the negative 24. Before, I still haven't integrated. I'm just trying to make life as easy as I possibly can before I integrate and evaluate. So I pulled out a negative 24. You technically don't have to do the negative. You could leave the negative in there, but since I pulled out the negative, that becomes a negative 1. Okay, now I can integrate. So that's x cubed over 3 minus x. Plugging in negative 1 and positive 1. So we've got negative 24 pi times 1/3 minus 1. Negative 1/3 plus 1. Change the signs and add. So we've got 2/3 minus 2, which would be subtracting 6/3. So negative 24 pi times negative, because I have positive 1/3 minus a negative 1/3, so 1/3 plus 1/3. And 24 over 3 is 8, and negative 8 times negative 4 is positive 32 pi. Okay, we are talking about volume. Volume should always be positive. I know we had some scenarios where area could be negative. Volume is never going to be negative. If you get a negative number, you need to go back and check something somewhere because volume should never be negative. Volume should always have a positive value. Any questions? Making sense? I see some yeses and some no's. Let's do a couple more. Right, you're adding. Okay, well, that's it. Oh, this? Because I was subtracting because it's my lower limit. It was a minus.
Well, why don't you just do like 1/3 minus 1?
Because I like to combine things that are fractions and combine things that are whole numbers and then get a common denominator. But that's fine. If you wanted to do that, negative 2/3 plus negative 2/3, still negative 4/3. You get negative 4/3. You should get negative 4/3 either way. That's fine. If you want to do 1/3 minus 1 and 1/3 plus negative 1, that's fine. Go for it. I just like to combine my fractions, combine my whole numbers, and then get a common denominator. Yeah. Okay. Well, good. That's the easy part. Okay. All right, let's look at this one. Find the volume obtained by rotating graphs of 9 minus x squared and y equals 12. So those are our two curves. You can see that in the first figure. Between 0 and 3, and we're going to do it twice. The first time we're going to do it around the line y equals 12. The second time, we are going to do it around the line y equals 15. Okay, so first time, y equals 12. Remember what I told you when you're trying to figure out your radius. Draw a segment from the axis you're rotating around. So we are rotating around y equals 12. Draw it to the furthest curve away. So that's my radius. Okay, that's my radius. I can draw a couple of them in here. Okay. From the axis you're rotating around, draw it to the furthest curve away. All right, so let's start to set up our volume here. Volume is equal to pi times the integral. They told us that it was from 0 to 3. Now, I don't have an outer and an inner radius here. Okay, this one is just because I'm rotating it around the edge of my region. So I just have to figure out an expression for my radius. Are these segments that I drew, are they the length that's the y value? Is the y value from this curve, does that give me the length of those segments? No. The y value of the curve is this part. This is my y value. From the x-axis to the curve, that's my y value. Okay. All of these go up to the line y equals 12. So if we do 12 minus the y value, we're going to get the purple part. 12 minus the y value is going to give us the purple part, which is the radius. So our radius is 12 minus our function, 9 minus x squared. Do I need to explain that part a little bit more? Do we see that? Okay, so when your axis is above your curve, then you got to take the axis minus the curve to get your radius. So let's see here. If we simplify this, 12 minus 9 is 3, and we're subtracting a negative x squared, so that becomes 3 plus x squared. And we are squaring it. So 9 plus 6x squared plus x to the 4th. Integrate 9x plus 2x cubed plus x to the 5th over 5. Evaluating from 0 to 3. So we've got 27 plus 27 times 2, so 54, plus 3 to the 5th, 243 over 5. We plug in 0. All those have x's, so that part is 0. So we've got 27 plus 54 would be 81. Yeah, 81 plus 243 over 5. We get a common denominator, multiply 81 by 5. That's what? 405? Yeah. So 405 plus 243 over 5. So 648 pi over 5. Well, unfortunately, they won't be there during the AP exam. Just for now. I might leave it out. All right, let's do the second one. Okay, this time we're rotating it around y equals 15. Okay, this time we're rotating it around y equals 15. So I'm going to erase what I have drawn on the first figure. Okay, so now if we're going around y equals 15, now we're going to have the washer thing. We got to subtract because we have a gap here. There's a gap between our region and the axis that we're rotating around. So start on the axis you're rotating around, draw to the furthest curve away. We've got to figure out the expression for that. Well, I think it's pretty obvious that it's similar to what we just did. It would be, this time it would be 15 minus the y value. Okay, 15 minus the y value would give us the radius there. So 15 minus the 9 minus x squared, minus our inner radius. So start on the axis you're rotating around, draw to the closest curve. You might want to draw a couple of these, but it doesn't matter how many I draw, it's the same segment every time, and it's length 3. So, not really that much more complicated than the problem that we just did. Let's see what happens. We got 15 minus 9 is 6 plus x squared. And we're going to square that. So that's 36 plus 12x squared plus x to the 4th minus 3 squared is 9. So we have x to the 4th plus 12x squared. 36 minus 9 would be 25. That's great. X to the 5th over 5 plus 4x cubed plus 25x. Evaluating from 0 to 3. 3 to the 5th over 5 is 243 over 5 again. 3 cubed is 27. 27 times 4 would be 54 times 2, 108. Plus 25 times 3, 125. Again, plug in 0. They're all zeros, so we really don't have to do that. 108 plus 125. What? 75, yeah. No idea where 125 came from. Good catch. Nope, didn't do that on purpose. No idea where the 125 came from. Okay, thank you for saving me before I kept going. All right, so that's what, 183. 183, when we put those two together. So then multiply by 5. I'm not going to screw this one up. 41, 915. Yeah, 915. So then 915 plus 243 is what? 1158 pi over 5. Bless you. Bless you. All right, we got time for the last one. Okay, what if we're going around a vertical axis? Okay, we've done the cross sections to the vertical axis, so it's not really anything earth-shattering here. Same principles, just in terms of y instead of in terms of x. Just in terms of y instead of in terms of x. So we are taking 9 minus x squared between 0 and 3, and we're rotating it around x equals -2. So the figure that I've got there pretty much, gives you the setup, but let's walk through it. We're doing it about a vertical axis, so we need to take y equals 9 minus x squared and turn it into x equals. So y minus 9 is equal to -x squared. Divide by that negative, so 9 minus y is equal to x squared. Take the square root. We are looking at the positive x values here, so we just use the positive square root of 9 minus y. So that gives us the distance from what they have labeled on this picture as a to b. Okay, that would be the square root of 9 minus y, the distance from a to b there. All right, so our volume is we're still talking about circles. Pi times the integral from, we're doing it vertically, so we start at 0, we end at 9. Okay, we start at 0, we end at 9 because we're going vertically. All right, so our outer radius, start on the axis of rotation, draw to the curve. So to figure out that radius, we've got our x value this time plus the distance from the y-axis to the curve is 2. So we've got the square root of 9 minus y plus 2. Okay, plus 2 because our region is below. If you turn your head to the right, the axis of rotation is below your region, so you're adding in that scenario, squared. Now we do have a gap. There is a gap between your axis of rotation and your region, so you do have an inner radius, so we have to subtract, and that inner radius is always 2. Because the square root of 9 minus y just gives me the distance in my region. My axis is way over here, so I got that whole distance. I got to take my region plus the gap. So the 2's don't cancel because we've got to square them, and they interact with other stuff. So we FOIL this out. The square root of 9 minus y times the square root of 9 minus y is 9 minus y. We have 2 square roots of 9 minus y on the outside and on the inside, so we've got plus 4 square roots of 9 minus y. And 2 squared is 4. So that one's a little bit weirder when we're FOILing out. And then, of course, 2 squared on the end is minus a 4. So we can mark those out. And if we integrate here, there's no simplifying that we can do. We just have to integrate. So we get 9y minus y squared over 2. Be careful with this square root. So this is 9 minus y to the 1/2. So add 1 to our exponent, that's the 3/2. Divide by 3/2, so that's multiplying by 2/3. So we get 4 times 2/3 is 8/3. I need a negative in front of that because that was a negative y. Okay, think about taking the derivative of that. You gotta apply the chain rule. You gotta multiply by the root of the inside, which is a -1, so I need a negative in front of that 8/3. So we're evaluating this from 0 to 9. So we get 81 minus 81 over 2. Guess what happens when we plug 9 into that 9 minus y? 9 minus 9 is 0. So that part goes away. Now be careful with the 0 though. When we plug 0 into 9y and y squared over 2, it doesn't equal anything, but it will give us something when we plug it into this part. So we're adding 8/3 times 9 minus 0 is of course 9. The square root of 9 is 3. 3 cubed is 27. So 27 over 3 is 9. Eight times 9 is 72. So we've got 153. So 153 times 2 is 306 minus 81 over 2. 5 225 over 2. Did I do that right? I hope I did all that right. Yeah, did somebody do the beginning part on the correctly? 81 minus 81 over 2.